Looks like we are at a quorum. And we're at the hour, so we can get started. So welcome to the FRB 2021 1B session. Perhaps you attended the 1A session as well. So these are the same program of talks as the 1A session. And some of them will be recorded, but some of them will also be given live. So we have some hero presenters who will be giving their talk twice. And I look forward to a very interesting session. So just to kick it off, my name is Emily Petroff. I'm currently in a joint position as a Vennie Fellow at the University of Amsterdam and as a project manager in the CHIME FRB collaboration in Canada. So I will be moderating this session, and I think it's quite fitting. I find it really fun and interesting to be that the first session of an FRB conference is just totally focused on populations. It used to be that the first session was always in FRB conferences was always given to talks about individual new FRBs that we found and how they were special and interesting. And this one has polarization, and this one has a high DM, and this one's really bright. And we've just completely abandoned that. And now we just jump straight in with the population in the very first session. So it gives you an indication of how far we've come as a community. And our first talk of the session will be given by Clancy James from Curtin University, who will be talking about the FRB population. So Clancy, take it away. I'll give you 3 minutes to 15.
Okay, thank you very much. Cheers, Emily, for the introduction. While I'm saying thank you, let me say a big thank you to the whole craft collaboration. I was telling Emily beforehand, I was very lucky to walk into my current position just as craft was detecting its first FRB. And in particular, thanks to my co-authors here. So yes, the FRB population. So what do I really mean regarding the FRB population, right? I tend to think of these topics, right? Are there more in the near or distant universe, more at lower high frequencies? How many are there? How many bright versus dim ones? I'm going to try to ignore all these little details that Emily briefly mentioned about, some do or don't repeat. What exactly are they like? What are their host galaxies? What's their emission structure? This is all annoying noise I'm going to try to brush under the carpet, and experts can tell you about that at other parts of the conference. I'm not going to directly talk about FRB cosmology, but for the purpose of this talk, this stuff, what I'm going to be talking about in population modeling is extremely relevant for FRB cosmology because this introduces biases in this, and I'm going to be shouting that loudly in the relevant discussion session. Okay, so we have out here somewhere in the universe our true FRB population, and then we have this annoying thing called a radio telescope that detects it, which is a biased instrument. It's an imperfect instrument. It's not a massless, frictionless pulley. So what we really have to do is work out how to get from these observed fast radio bursts here back to the true FRB population. Because what we observe are a distorted fraction of the population, and there might be many possible true populations, right? Many different kinds of things here that could explain the same observations. So fundamentally, there's only one way to do this, right? The correct approach is to model these biasing effects, vary your unknowns, like vary this, and see what matches this after doing those biasing effects. So this was advocated by Liam Connor and was first implemented in modeling by Ray Lau, right? I'll point out that many authors have actually treated these biasing effects, but the full process of doing a fit to data over full variation of the population model, as far as I know, was really done by Ray first. Okay, so we need to understand this. So I am not going to go into the full details. I just want to give you a taste of what this looks like, right? Let's imagine we want to estimate the rate of FRBs detected by an experiment, right? So you've got some expected number of FRBs given by, the time of the experiment times the rate. Well, you've got the rate, you've got to integrate over the volume of the universe here, right? Cosmological factors there by your source population, right? It might be different amounts in the near universe versus the distant universe. Your threshold depends on the dispersion measure, right? You have a different response. So you need to integrate over the dispersion measure distribution. So this is cosmological smearing, host galaxies here, etc. Your telescope has a beam shape. Anyone in CHIME definitely knows your telescope has a beam shape, right? But even if you've got a nice Gaussian beam, you have to take that into account because the parts of the sky are viewed at different sensitivities, right? So this is the area of sky viewed at a given sensitivity. You have to care about your distribution of, well, let's call it burst width, but more generally, microscopic properties of your FRB, because for a given amount of energy, wider ones are less easy to detect, or for a given luminosity, wider ones are more easy. And then you care about your intrinsic luminosity function, because once you've got your threshold, which is a function of where you are on the beam, the width of the thing, the redshift it's at, and the dispersion measure, well, how many FRBs are, above that threshold? Right? So this is assuming a homogeneous universe, and see the talk by Mawson later about what happens once you lose this assumption. Again, sweep that under the rug. And you can do analogous calculations modeling these aspects, right? But one thing I really want to point out is that this expectation for the number is a sum over all bursts, regardless of whether or not they're coming from repeaters or once-off things. However, if you ignore repetition, these are all independent things. So it comes to a Poissonian distribution, right? Your probability of observing n things for an expectation. Once repeaters are in there, yeah, it's nasty. So regarding repeaters, we have to remember that the worst biasing effect of all we have is us, right? We have control of the telescopes, we point them at interesting things, and it means that the future observations are based on past observations. That's terrible statistics. The CHIME collaboration was extremely intelligent. They bolted their telescope to the ground with these nice metal struts to prevent intelligent astronomers from pointing it anywhere differently. So there's no possibility of biasing your statistics like that, right? And we also have to remember that the only FRB survey to ever detect a repeating FRB is CHIME, right? All the others have been detected in targeted follow-up surveys, where it was first detected in one survey, then someone else specifically targeted that region to search for follow-up bursts, right? So in this talk, I'm going to be concentrating on ASCAP and Parkes, right? And so they have not observed such repetitions. Now, repetitions will matter when you spend a long time looking in the same patch of sky with one instrument. We'll get back to the effects of that later. Now, the other nuance that I want to highlight that isn't so often discussed is this annoying interaction with the FRB spectrum. So ASCAP observations, tended to see either broadband FRBs or FRBs that were modulated by, some kind of speckling structure. And JP modeled this in this paper with, a frequency spectrum that looked like the fluence was proportional to the frequency to the power alpha, with alpha being about minus 1.5, right? Very broadly. And this affects your the implied energy because you get your K correction, right? Due to the emission being at a different frequency to observation. However, if you looked at, let's say, this FRB detected by Pragya with Parkes, over 4 gigahertz, it's present in about 50 megahertz. And if you said that this thing looked like a power law frequency spectrum, you are insane. I'm sorry, it's just a fact. And CHIME have then since done a more comprehensive analysis. And you see that, sure, a reasonable fraction, I think at 60% from memory, are sort of relatively broadband bursts, but there's others that a significant fraction of the population are narrowband. So if you think of these kinds of bursts, you should describe it as a frequency dependent rate, right? And it turns out that the Macquart result actually gives you an alpha of minus 0.65. You have to change the index from the minus 1.5 for this behavior, all right? So the truth is really a mixture of these scenarios, but you have to model both because we don't really not have a very good understanding of the behavior. So this was applied to ASCAP and Parkes observations. I want to note that, we had nice beam patterns here. Turns out modeling this as a sum of Gaussians over the 13 multi-beams is pretty good. Modeling the ASCAP observations as Gaussian, it's not as wrong as modeling them as, I don't know, my handkerchief, but it introduces problems because the beam overlaps, and that's very significant. Now, I was fitting the number of FRBs detected, DM and Z distributions, and signal noise thresholds, but with some caveats, you can't blindly get these observations and then assume you're getting an unbiased sample. So you have to pay some attention to what you choose. And all these observations were L-band, which helps to control for some of these biasing effects from alpha. So one of the fundamental issues is, as I mentioned, you don't have much way of getting a handle on alpha. So let's imagine you want to model less FRBs at high redshift, right? You can do this in three ways. You can have slow source evolution, so there's not many there. You can have a significant K correction, so that they're much dimmer, right? Or you can have a low Emax, right? Low maximum energy, so you just can't observe them, right, from that distance. And from a modeling perspective, it's difficult to tell the difference. So you see here we've got, this is increasing redshift evolution here. This is star formation rate. Here we have increasing maximum energy, and here we have this alpha. And you see there's this broad region of degeneracy. So you really have to, at this stage, apply a prior, right? Hopefully we can get around that in future. So one result of doing this, so we were modeling the star formation rate, using the McDowell and Dickinson model, and smoothly varying it with n, right? So n equals 0, no source evolution. N equals 1, star formation rate. N equals 2, stronger than that. And, well, the first thing you need to know is that your results depend on whether or not using this spectral index interpretation, right? Or you're using this rate interpretation. In blue, we have the results with this sort of, without the Gaussian prior, without this prior on alpha. It's a very broad uniform prior, I guess. And in this yellowy orange, it's with the Macquart et al. Prior. Now, almost no matter what you do, you exclude no population evolution unless you have this interpretation with no prior on alpha. And we do. It's a good prior. We should use it. So the results are all consistent with evolution with the star formation rate, but we don't have a very good handle on it. So the FRB population does evolve, but we're not really sure how. And there's apparently a missing bracket here. Okay. So that's sort of result number one. Result number two, when you do this, well, we look at the luminosity index gamma. So if we, I just realized I cut out a slide that shows this. So the luminosity index gamma is the cumulative luminosity index. So the number of FRBs above some energy E goes with E to the gamma, right? It's not the differential index, which would be gamma minus 1. So with this parameter, you have and I was using a power law model here, up to some Emax. So your magic numbers here is that if gamma is less than minus 1.5, your FRBs are mostly seen near some minimum energy in the nearby universe. And that's excluded by the fact that we see FRBs mostly from the distant universe. If gamma is flat, right, it's greater than minus 1, you see the FRBs mostly near Emax from the very distant universe, and that's sort of the common expectation. But there's this intermediate regime where FRBs get generally spread out, but there's a small excess in the local universe. I'll show you an example of that later. And so we get constraints that are broadly consistent with this intermediate case, although we can't rule out the flat distribution. And this sort of seems consistent with CHIME, observing some FRBs in the very local volume, right? It's a very small local volume, right? Not much space between us and M81, but, even 1 in 3,000 or so FRBs is relevant. Now, there is some tension when doing the modeling. So if we look at this plot over here, this is a histogram of ASCAP localized FRBs and their measured redshifts. In orange is this best fit prediction, right, for what we expect for the redshift distribution. And you see this little bump up here, this little kick up in the nearby universe due to gamma being less than minus 1, right? Now, clearly, all these predictions have an excess here beyond observations. You can try throwing in a minimum energy that's significant, so and try to increase your minimum energy, and that only does so much. You can't increase your minimum energy much more before you run up against other problems. And within the error bars, we can't really explain this, so there's some tension there. But this could be due to either statistical fluctuations, right, 7%, maybe this high minimum energy, perhaps, or a turnover in the luminosity function. So this paper recently came out that was presented at FRB 2020 by D. Lee et al., showing how for FRB 121102, we have this power law-like behavior at high energies, but then it sort of flattens and maybe turns over at low energies.
3 minutes, Clancy.
Was it 3?
Yes.
Yeah. Okay, I will skip this part then, but suffice to say you might expect such behavior due to the influence of repeating FRBs. So I know, screen capture that slide and I'll move on. Going to skip over the results for the Galaxy DM because I want to talk about this famous plot, the Macarthur Relation, right? Named in honor of Jean-Pierre. So this plot is really looking at the probability of a DM given a redshift is consistent with the baryonic matter density of the universe. So mean density is the black line, localized FRBs are these points. Redshift x-axis, DM y-axis. And great, they cluster about this line. I would argue that this is a wonderful case, right? When people saw this paper, they think, fantastic, this shows we can use dispersion measure as a proxy for redshift. Now, this is the power of drawing a line. Because if you take this relation and you just, move it around, so you've got DM on the x-axis and redshift on the y-axis, and then you ask, we measure an FRB with some certain DM. What's its redshift? Well, look, we got one with a cosmic DM of 300. Redshift is from 0.1 to 0.4, right? So this is not a one-to-one relation. It is very far from a one-to-one relation. And so using DM as a redshift proxy is extremely poor, right? Now it actually gets worse, right? So it turns out that here we've got a color plot for the probability of redshift given DM, right, from this model we came up with. Now for a nearby DM, you do roughly follow the Macarthur relation. This is offset because it includes the host galaxy, right, the host galaxy here. And most go above it, but then above a certain redshift, above a certain DM, you actually expect for higher DMs to get a lower redshift. So why is that the case?
1 minute.
Well,
Clancy.
1 minute? Yeah, thanks. So here we have a joint probability distribution for redshift and DM, right? And here, this is our maximum redshift at which we can see an FRB due to some maximum energy. And this implies a maximum DM for the Macarthur relation. But if you get your redshift at less than the maximum redshift, you can still have a higher DM, right? Due to the influence of, let's say, passing through a lot of matter. Might not be a high likelihood, but still probable. So essentially, what happens is that the nature of this, right, depends on the parameters of gamma and Emax and observation bias, right? But so we're not sure exactly where this turnover in the Macarthur relation is, but it absolutely is 100% guaranteed to be there for some fraction of a large FRB sample. And if you looked at this plot from Shannon et al. Back in 2018, which seems a lifetime ago, these three FRBs here might be likely candidates for ones affected by that. So the conclusion here, just this modeling is difficult, but you've just got to do it properly, right? There's some key takeaways about FRBs being maybe more local than expected, but I've already told you about that. My specific wish list, CHIME have done an excellent job of modeling their selection function. Please publish it. It'd be great. I'd love to use it. More fast FRBs, maybe from the distant universe. And there's an ASCAP FRB, which has a DM of 1785.3 parsecs per centimeter cubed. We haven't localized it yet. My guess is it comes from a redshift of less than 0.8. And my final word, really, which is the more important, honestly, than anything else you hear at the conference, because global warming's a thing and nobody's going to fund astronomy if they're too busy dealing with a world in crisis. So we can actually affect this, right, with our astronomical behaviors, and we can try to change this. So thank you very much for making this a virtual conference to the organizers. It's wonderful. And if you want to help advocate for climate action, Astronomers for Planet Earth will help you do that. So thank you very much, and I'll pass to questions.
Thank you, Clancy. Okay, so we have one question in the Q&A, a couple questions now, and then I see one in the chat as well. So first from Ben Snappers, he says, very thought-provoking. How much does our uncertainty on the galactic DM contribution affect the possibility of missing those FRBs in the kick-up region? Similarly, effects of RFI on lower DM sources too, if the band is relatively narrow.
Yeah, so my view is it's probably more about the RFI. So I think in initial FRB searches, it was probably the uncertainty in the galactic contribution where people were being quite, they weren't really sure about FRBs, so they had to be very certain to make sure that they were excluding any possibility of it being galactic. Now, I think it's really selection effects against, 0 DM RFI. That's certainly the case for ASCAP bursts at the moment. Yeah. And I expect it's similar for CHIME.
Okay. All right. And then we have time for one or two quick more questions. So Sri Harsh asks, in the Macquart relation, 6 out of 8 FRBs fall on one side of the mean line. Is that a statistical fluctuation or possibly a selection bias?
It's neither, it's expected. And that's simply because you've got the mean, right? But the mean is not the median. And because most of the universe is not very much, but a small amount of the universe is quite a lot of matter. It means that, matter is very clumpy. And so most of your FRBs, you expect to live just below the Macarthur relation here. So this is the 7 that I modeled, and you expect most to be just below here. But then the ones that are above might be very far above, right? Imagine an FRB coming from the center of the Virgo cluster, for instance. You would detect that somewhere right up the top here.
Yeah.
So yeah, if neither.
Great. Okay, and then one quick last question. Is it correct that if many yet unlocalized FRBs are actually relatively local on the cosmological scale, then they are related to dwarf galaxies?
I mean, it might be correct, but I think that's a different question. I think that you can easily have, you're certainly correct though, that if there's lots of unlocalized ones that are very close, right? If they were very close and they were associated with big galaxies like Andromeda or, some very well-known thing, then they might have been highlighted already in the literature.
Right. Okay. I think there's one more question in the chat, but I will copy that into the Slack channel for you. So we can move on to the next talk, which is a recorded talk by Nidhi Saini, who was in our first session talking about if there are two distinct populations of FRBs. I don't think I hear any audio. I don't know if other people do.
Sorry, my mistake.
It's fine, I guess. Yes. Okay. Good morning, everyone. My name is Nidhi Saini, and this work is done with Professor Kartik Dasgupta. So let me just start. So everyone now knows what are FRBs. They are just high intensity millisecond duration of radio pulses. They have been detected just a decade ago, and now they are making noise everywhere, right? So their peak flux density is, so these values are taken from the catalog, is ranging from 0.04 to 600 Jansky at a given frequency of 400 megahertz to 2 gigahertz. And the typical dispersion measure is found to be very high, which is ranging from 100 to 2500 parsec per cubic centimeter, which gives you an idea about their distance or distance of the source to the FRBs. So they are found to be extragalactic, assuming the model for electron density for Milky Way. And obviously, the value of dispersion measure for the given line of sight is supposed to be very high for FRBs to encounter the Milky Way part only. Now the brightness temperature is also very high, which is greater than 10 to the power 35 Kelvin, which gives you an idea about the coherent emission of the source at the source for the FRBs. And the rate is expected to be 10 to the power 4 to 10 to the power 5 giga per cubic gigaparsec per year. And now this study that I'm going to show you is based on 140 FRBs with 20 repeaters. Okay, so just this very simple histogram for fluence gives you a bimodality in fluence. Obviously, the every FRB is detected at different frequencies. So just to putting every FRB on the equal footing, what we have done is we have scaled down the fluence to 1 gigahertz. And the alpha is taken from this study here, Marquardt et al. 2018, which is minus 1.6. You can see that there is a dip which explains the bimodality. Now, we have taken different values of alpha, and this dip is consistent with different values of alpha. So, which gives you a hint that there might be two kind of FRBs or bimodality, obviously bimodality in the population. Now, fluence is not a very good parameter to find, to say something solid about the FRBs. So we have moved on to the total energy emitted from the FRBs, which gives you the intrinsic properties of the FRB source. Now, just plotting the very simple histogram for energy as well. This is also giving you a tip in the histogram, which gives you an idea that the bimodality that we were talking about is true in sense. Now, this dip is around 3 into 10 to the power 41 hours. Now, let us divide the whole population set for FRBs into two categories. One is population 1, which includes low energy FRBs, basically all the FRBs having energy less than 3 into 10 to the power 41 ergs, and greater than that, they'll be called high energy FRBs. Now we have studied different statistical statistical tests for the two populations. In figure 1, you can see that the CDF for the two population for the total energy of the FRBs. Now, this separation in the CDF also gives you a hint that they might be coming from the two different kind of data sets. And Anderson-Darling test supports that the two population, that the two samples that we are talking about is coming from the two different populations. They do not belong to the same data set. And then we have run to the fluence as well, then luminosity. All the CDFs are showing that the separation is true in the sense based on the Anderson-Darling test. And the lower plots are just showing the corresponding PDFs for the same parameters. And then dispersion measure, dispersion measure also shows that the null hypothesis that we have taken, that the two populations are coming from the same data set, is ruled out by the Anderson-Darling test. The second plot is showing the corrected pulse width, which is basically pulse width divided or the redshifted pulse width. Now, these all tests, these all CDFs ensures that the two populations are completely different. They do not belong to the same wide range of the population. And also, just one thing here, which shows that the brightness temperature, the last figure, spans the whole same parameter space for the two populations. So brightness temperature does not show any wide range variety in the values of the two population FRBs. Now, these are the statistical test table, Anderson-Darling, and also we have done MWW test, which also supports the two population theory. We have also done some correlation tests based on the different parameters, estimated parameters, as well as the provided parameters in the dispersion measure with total energy, which shows a correlation coefficient of 0.5. And they show that obviously they will be dependent on each other because total energy gives you the distance and the total energy are related somehow. So similarly, then luminosity and total energy will also depend on each other, and they show a strong correlation. The main point is that we have calculated or estimated the total energy, and which is theoretically intrinsic parameter, and it depends on various other parameters that are given in the catalog. So it's like we are trying to find dependency so that we can figure out if there is any correlation which can give hint towards the two population kind of thing. And the pink dots represent the population 1, the blue dot represents the population 2, and repeaters are marked differently. Right? You can see in the figure number 3, dispersion measure versus luminosity, which shows a distinct pattern in the plot. like we could find, if we could find, I mean, now we have more data sets, so we are trying to do the same study with the new data set, with the CHIME catalog data set. And you can see that dispersion measure and luminosity also have a Pearson coefficient of 0.42, and they are obviously correlated. Then the brightness, temperature, and luminosity, which are which shows the Pearson coefficient of 0.44. Now the next thing is brightness, temperature versus fluence, which is scaled to 1 gigahertz. This shows, this plot is very interesting in a sense that there is a, if one can see, there is a clustering at different centers, like low energy repeaters are falling down, but if you can see, all the repeaters are in the low energy region, right? Now, there is a clustering at the lower end left corner of the plot and the right corner, right upper corner of the plot. So, if we are just trying to figure out why this clustering is happening in this particular plot. Now, brightness, temperature versus redshift shows negative correlation with minus 2.7. Then dispersion measure. This is an obvious plot. Dispersion measure versus redshift, which shows a very strong correlation of 0.9, and corrected pulse width, which is basically redshifted pulse width versus luminosity. Here also, just similar to the energy versus corrected pulse width plot, the low energy region, low energy FRBs are falling in the lower end of the plot, lower left end of the plot, and high energy are falling at the upper side. Now, this plot shows a very weak correlation, but if you just see this plot very carefully, we have calculated the Pearson coefficient for two different plots for the scatter, all the scatter plots, and this particular plot shows that there is a sign changing in the slope or the Pearson coefficient of the two populations, which might also hint towards the the two set of categories of the FRBs. Then we have done the source count of FRBs. Consider there is a spherical shell of thickness dr. Number of sources in this shell is dn. So dn will directly proportional to dr. And if we just calculate number of FRBs up to a distance r, this will be given by relation number 3. And the peak flux depends, peak flux and luminosity relation is given by equation number 4. Now, using the two equation, we can calculate easily the number of sources up to a distance r, which can be shown differently in a way by equation number 6. Hence, if we just talk about differential source count, the slope should be minus 1.5, right? But what we have find is that, okay, so there is a mistake in the caption. It is 118 FRBs because we have excluded Pushchino FRBs, and the remaining, and few of them do not have the data set, all the parameters in the catalog, like pulse width is null and other things. So if you can just
3 minutes remaining.
Okay, I'm just almost done. So you can just easily see that this differential source count, which should have a slope of minus 1.5, does not satisfy. There is if one carefully find that there is a two slope, one can easily fit two slopes in the source count, right? Another way of depicting the same plot is that multiply this number, which is y-axis, by fluence to the power minus 1.5 and plot it with fluence. Now, the second plot should have a parallel line to the fluence, but it shows a evolution in the population of FRBs. Now we are trying to figure out if this two-slope thing can also, give hint towards the two, whether the two population that we are talking about in previous study, population 1 to population 2, have two different kind of slopes, which is under study basically. So the summary says that we find bimodality in humans as well as energy histograms, which hints towards the two different kind of FRB populations. Anderson-Darling test and MWW test also supports that the two populations actually exist. Various correlation plots have been shown, which are going to be further studied. All the repeaters, all the repeaters are falling into the low energy population. The two population study is very significant to predict whether the two populations are coming from two different kind of progenitor models. If we can correlate that, that will be very interesting to show. Then now the study that we are taking to the CHIME first catalog. We are trying to figure out if CHIME, only CHIME FRBs show different behavior than the total of FRBs. So this was from my side. Thank you.
Okay, that was Nidhi's talk. I don't believe that she is online for questions. Let me just check. Nope. We've had a few questions and discussions going back and forth in the Slack channel, so I encourage you to have a look there. I think I can maybe just highlight one of them, which is a question from Sergey Popov, who asked if can the bimodality that you talked about be related just to different sensitivity of different instruments? And I think this is very possible that it could indeed be just an instrumental effect that is producing this type of bimodality. So that just taking into account the instrument response may in some sense account for some of these distributions. So that's something that I imagine Nidhi will look into. But if you have further questions for Nidhi, I encourage you to put them in the Slack channel and tag her, and then when she's online, she can get back to them. So please have a look at the discussions that are happening in the Slack channel. Okay, then we will, unless there are there other questions, I don't see anything in the Q&A, but give people a chance to type something. Okay. All right, well, yeah, so please, if you have questions about Nidhi's talk, I encourage you to link up with her on Slack to ask some questions, or maybe at a coffee session or something like that. So, okay, in that case, I think we will move on to the next talk from this session, which will also be a recorded talk, but the speaker is present at the session to answer questions afterwards. So if you have questions for Mawson Sammons, who's from Curtin University, please put them in the Q&A, and he can address them at the end of the recorded talk. So the next one is from Mawson Sammons about the effects of gravitational lensing on fast radio burst source counts.
Thank you very much. So yes, I'm a PhD student under the supervision of Cathtrot, Clancy, Mark Walker, and the late and great JP. And so yes, I'd like to kick off with a rather simple example. If we consider we have a population of sources that are all at a constant luminosity, and then we kind of represent these sources visually as randomly distributed about some central observer, then any observation that we take of these sources is going to have some sensitivity or flux threshold, which defines a region in space within which we can observe our sources and outside which they are too faint for us to see. Now, gravitational lensing can apply a magnification that boosts the observable flux so that we might see sources from beyond this kind of physical boundary. This is going to change the shape of our luminosity function, as we'll get contributions from sources with apparently higher luminosity than we would have intrinsically expected. Now, understanding this kind of effect is important because we observe this lensed distribution rather than the intrinsic. and each of the components that go into it can tell us something about the properties that go into it. Namely, the intrinsic distribution of FRBs is quite important, as we just saw, for kind of finding out things about the intrinsic population and emission mechanisms, whereas the magnification PDF that gets convolved with this intrinsic distribution to give us what we observe depends upon the universe's mass distribution. And so if we want to find out things about the properties of dark matter and whatnot, this property can be quite helpful. So this gravitational lensing PDF is effectively the probability that our source FRB here is going to be magnified by some value mu. Now, if we visually represent this as red ellipse cross sections to lensing at a magnification greater than mu, and to have our FRB source here, which currently falls short of our observation, if our source is then seen from behind one of these cross sections, its flux gets boosted and we'll be able to observe it. So clearly the probability that we're going to lens this source depends upon these cross sections greatly. In previous works, what has been done is these cross sections have been mapped from their local lens plane into the source plane, and the fraction of the area in the source plane that they occupy gives us the probability that our source will be magnified by some value. Now, the mapping between the local lens plane and the source plane is a little bit more complicated than a simple projection, but nonetheless, the essence of what's going on is captured in this kind of graphic. And this model is quite good for the scenario we've got here. We have a low number of lenses. There's no overlap between their projected cross-sections on the source plane, and they're quite far separated from one another. However, if we start to remove our source FRB and place it more and more distantly in the universe, we expect more and more lenses to come along the line of sight, and we might end up in a regime that looks a little bit more like this. Now, as our source passes by more than one of these cross-sections, we go through what is called multiple lensing, which is a highly nonlinear process that's really only suitable to treatment via a numerical simulation. Now, numerical simulations are quite often computationally limited, so in this project we wanted to see how far we could get with an analytical calculation alone. So to get ourselves out of this situation and back into a realm that can be treated analytically, what we can do is recognize that as we place our source further and further away in the universe, we require a higher and higher magnification for it to remain observable. As we increase the magnification, the cross-section of our lenses gets reduced drastically, and so we can happily remain in a kind of low optical depth regime where there isn't too much overlap between our cross-sections. However, no amount of reducing the cross-section size is going to change the separation between our lensing objects. Now, if we want to treat a rather large number density of lenses, we're going to need to kind of treat how these objects interact with each other gravitationally, as they'll affect the shape of each other's cross-sections. This can be known as shear, whereas convergence or Ricci focusing gives us the traditional magnification of a source image. A shear can result in a distortion or a stretching of that image in one direction. As we see here in the famous Cheshire Cat lens, these external galaxies have been stretched quite severely around the outside. Now, treating this shear has been done previously. In 1984, Nityanand and Ostraker found that for a two-dimensional screen, we can place an arbitrary distribution of point lenses that all contribute to the shear of the ray in the middle, but we can find an analytical and completely nonlinear solution to this problem. Now, this is quite good if we wanted to treat the lensing for a distribution of, say, stars in a halo, as a halo is quite well approximated by a thin screen. However, if we wanted to take on something a little bit more complex, such as an extended three-dimensional distribution of, say, primordial black holes in the intergalactic medium, we're going to need to take this treatment a step further. This has also been done previously by taking a host of these kind of lens planes and stacking them back to back, then processing our ray in a simulation sense through this stacking of screens. Now, if we wanted to avoid the simulations, like we said earlier, we can make some simple approximations to take the discrete stacking of lens planes here to the continuum limit and give us a PDF that includes the shear for an extended three-dimensional distribution of point lenses. Now, this approximation that we make here removes the fully nonlinear results of this calculation. However, we still get out an approximation of the shear, at least to the first order. Now, as we said before, the low magnification regime is where our model is going to start to run into some trouble. So clearly we can't use all of this treatment. However, what we can do to have our model remain functional is we can crop our model at some suitably low or some suitably high magnification where it's still usable, and substitute the remainder of it for a delta function that is constrained by these integral constraints to our probability distribution function, namely that it has to be normalized to a value of 1, and the expectation value of our magnification has to match the area average magnification of the universe at that redshift. So now what remains is to determine this area average value. And to do so, we kind of need to understand how cosmological distances play into the mix. So traditionally, if we assume a homogeneous universe where matter is smoothed out everywhere, as is the standard, we get a very intuitive picture of the angular diameter distance given by these magenta lines, where an observer sees the source object here in the blue. And the density of matter within this beam is the same as the outside, so we get, yes, these very straight kind of unperturbed lines. However, as we start to remove matter from the inside of this beam and place it outside, the density on the outside becomes greater, and our lines are likely to get deflected away from the observer off to this denser part of the universe. This means that what the observer is going to see is these black deflected lines, and if we trace tangent from the observer's point of view, their angular size of the source is going to be greatly reduced with respect to what we would expect for the source's physical size. Now, the angular diameter distance is given as the physical size of the source over its perceived angular size. And so with a much reduced angular size, it appears as though our source is at an apparently larger angular diameter distance. In a slightly more intuitive picture, if we set up a kind of a toy universe here, where this eta fraction describes the portion of our matter in our universe that is homogeneously distributed, here we have the standard assumption picture, where we have our very easily understandable angular diameter distance with the density inside the cone that's identical to outside. However, if we start to take some matter from this pool of homogeneity and congeal it into compact objects, we end up with a separate distance known as the empty beam distance. This empty beam distance avoids the clumps, and so we'll experience a density of matter within its beam that's lower than the outside, which extends its angular diameter distance apparently. If we continue to reduce the fraction of smooth matter we have all the way to 0, this is going to extend even further. And so what is the ultimate difference between this empty beam distance and the homogeneous angular diameter distance that we traditionally think of? Well, it turns out that if we evaluate these two cases in the extreme, so our clumpy universe is the orange and our completely smooth universe is the blue, in the nearby universe, there's not all too much difference, but at higher redshifts, we start to notice there is a large discrepancy between the two. This is kind of important because the ratio of these distances squared is what gives us our area average magnification in the universe. And so at a high redshift, we might expect this value to be quite large. Now, all that remains now is to kind of investigate how do we determine this eta value and what is it for our universe? Well, it's a little bit complex because it actually depends on the scale of the observation that we're taking. This can be understood as if we consider this purple magenta line here, for a rather large angular size of source, these small-scale compact objects, which are small-scale inhomogeneities, are going to be averaged over by this observation because they're quite granular with respect to the volume of this beam. This means that the density of the cone inside is going to be the same as outside, and we get back the very standard picture of our angular diameter distance. However, if we have quite a compact object, we might expect that the density will fluctuate quite highly, and so our angular diameter distance might shift with position. Now, currently, observations tell us, such as the dispersion in the MZ relation for supernova, that the universe is approximately smooth with an eta value of 1. However, a canonical supernova has a co-moving volume in its beam of about 1,000 parsecs cubed, which is quite a bit larger than the volume to a canonical FRB, which is about 1 astronomical unit cubed. And so we can see that we're going to probe vastly different mass scales here. What are these mass scales? Well, if we take these co-moving volumes that's subtended by these canonical sources, and we multiply it by the average density in our universe, we get out a mass, a characteristic mass for this beam. If our inhomogeneities are larger than this characteristic mass, we expect less than 1 per beam, and so the universe will appear inhomogeneous. From the constraints from supernova, we can say that we don't really expect any heavier inhomogeneities than about 10 to the negative 5 solar masses floating out in the intergalactic medium. But below this, it's anyone's game. For FRBs, they probe a much greater range of inhomogeneities than supernova, and so we might be able to say something interesting. Namely, this shaded black region here is the currently unconstrained region of primordial black holes in literature. And so FRBs might provide us with a way to explore an entirely unconstrained region of dark matter parameter space. Now that we have a way to treat these eta values and so we can calculate our area average magnification, we can complete our model and actually now get out some source counts. So in this plot here, we've got on the y-axis differential source counts for a lens population normalized by the differential source counts in an unlensed population. On the y-axis, we have flux of our observed source normalized by the flux that it would have if it were at a redshift of 1 in a completely smooth universe. The two plots here are for a nearly smooth universe with a smooth matter fraction of 0.99, and for a universe that has 100% of its matter in compact objects that form our lenses. Now we can see, as expected, that our nearly smooth universe effectively matches the unlensed case at a 1-to-1 ratio. We see the eta equals 0 case has a rather different shape. Now for all the values left of about log s
3 minutes
1,
left, Mawson, 3 minutes.
Oh, thank you very much. For all the values left of about log s of 1, we can kind of ignore the shape of this because this is somewhat an artifact of the process. In this calculation, we only placed source objects out to about a redshift of 10, which means that as the magnification goes up to infinity, we can no longer continue to lens source objects into our account. However, in the nearby universe, we see that even in this extreme case of 100% of our matter being in lensing objects, we still only lens it at about a few percent. So this means that lensing might not be all too important for what we're considering. However, we can temper this kind of result with the knowledge that, as we explained earlier, this is for a very simplistic delta function distribution, and we're only calculating bolometric quantities in this kind of very preliminary work. So what we'd like to do now is extend this to a more realistic picture with a non-delta function luminosity for our sources, some spectral dependence, and we'd like to begin working with observables that are much more FRB-like, such as fluence and energy as opposed to flux and luminosity. And once we've done this, we can start getting out a picture of the lensing that is a little bit more realistic and see if it has more of an influence than it did in the simple delta function case. Some of this work is being baked into publications at the moment. There's one submitted and one to follow. So thank you very much. A little bit under time, but leaves more time for questions if there are any. Cheers.
Thanks, Mawson. We have one question from Hassan, who is asking.
Well, we'll have to wait for that question. If there are questions in this session from Mawson, please put them in the Q&A. I don't see any yet, but I know it can take some time to type them up. Okay. Surya has a question for you, Mawson, which is there any characteristic feature of gravitational lensing we can look for in localization maps?
Okay, interesting. So I guess like to have gravitational lensing, you obviously need masses to do that kind of lensing. So if you're looking at kind of an image with a dot on it that is the localization of your FRB, you can start to ask questions about, well, do we expect the kind of lensing objects that we need to be present in the environment that we've localized our burst to? Because of course, if say we've localized our burst to a galaxy, there are two options here. It could either be that the burst has originated in that galaxy, or that the image that we're seeing of the burst has actually been lensed by an object in that galaxy from something behind it. So we can look to those environments to say, you know, is there primordial black holes present? Do we expect a large kind of population of compact objects that could do the lensing we require? So that's kind of something you can get out of localizations. I know especially there was some results recently where objects had been, there was an FRB that was localized to a globular cluster, where we do kind of expect there to be a large population of older stellar mass objects that might be able to do the lensing. And so in that kind of situation, you can start to ask questions of, well, is it realistic to expect that you know, we're doing the lensing that we might require in these kind of cases? So yeah, I think that's probably all that you might be able to get out of localization maps, at least. There are definitely other characteristic features you can look for, but yeah.
Nice, thank you. There's a question in the Slack channel from X, which is, what are the subtleties, challenges of modifying the analysis from luminosity to fluence?
Yeah, right. So as you can kind of see, I've actually placed it on this final slide that I've got here. One of the complexities is that, well, so there's kind of two layers to this. For starters, you need to jump from having a bolometric quantity to a spectral quantity. And that has, you know, the nuance of having to introduce K corrections and the like. And then jumping from something like a spectral luminosity quantity to a fluence, you just effectively swap out the kind of equations that you're using. So rather than having the simple like L over the 4 pi times your luminosity distance, you have to introduce a little bit of redshift and the emission time, because obviously those quantities are going to change as your source gets cosmologically dilated between its emission and our observation. So that's kind of one of the nuances, is that your burst is only so wide, but that width and its bandwidth are going to change as the universe expands between observation and emission.
Okay, great. And then we have one other question in the Slack channel from Sriharsh. If we see a huge outlier in the isotropic energy versus DM as a proxy for redshift space, would that be a sign of a candidate lensing event, or is that a bit too naive?
I mean, it could be. So it's interesting in that what you kind of expect is that some of your fainter objects might be the ones that have been lensed, in the sense that if you have a very low observed flux, you tend to probe a much larger volume. So that gives you a much higher probability to lensing, because you just have a higher likelihood of crossing across something in that volume. So I don't know if I would naively expect that it would be kind of an outlier in that sense. I think it can pretty much look like any other burst.
Right, okay. And then one final question, since we have just a tiny bit of time, from Calvin in the chat. What are the total magnifications required for distorting the source count distribution?
Yeah, well, I suppose so. Effectively, for this kind of delta function case, what happens is when you have a magnification, you place that source at a higher distance. So any amount of magnification can change the shape of your luminosity function. What it actually depends on more drastically is the slope of your intrinsic luminosity function. So if you have quite a steep luminosity function, you can expect that shape might change quite dramatically. Whereas if you have a rather flat, if you had a completely flat luminosity function, you might not expect it to change at all.
Great, thank you. Okay, if there are further questions for Mawson, please put them in the Slack channel, and then maybe Mawson can address them there.
Yeah, look forward to it. Cheers.
Yeah, thank you. And okay, so the next talk will be another recorded talk, but our speaker is present. So if you have questions, please put them in the Q&A. So the next talk is by Pragya Chawla from the CHIME FRB collaboration and based at McGill, who will be telling us about the first CHIME FRB catalog.
Okay, hello everyone, I'm Pragya. I am working with the CHIME FRB collaboration. And today I'll be talking about the first CHIME FRB catalog that was recently released, but I will be specifically focusing on the interpretation of the dispersion measures and the scattering timescales of the bursts in the catalog. So briefly, CHIME is the Canadian Hydrogen Intensity Mapping Experiment. It is a transit telescope located in British Columbia in Canada, and it comprises of 4 cylinders, each 100 meters in length and 20 meters in diameter. Each of these cylinders is fitted with 256 dual polarization antennas, which are sensitive in the frequency range of 400 to 800 megahertz. The field of view of each of these antennas is about 250 degrees, extending 120 degrees in the north-south direction and ranging from 1.3 to 2.5 degrees in the east-west direction. So the inputs from all of these 1024 antennas are combined with appropriate phase delays to form 1024 beams on sky. The data for all of these beams is searched in real time with a frequency resolution of 24 kilohertz and a time resolution of about 1 millisecond. Since CHIME is a transit telescope and only observes directly overhead, all of these beams are located in a small strip of sky that is located directly overhead. The map on the right shows the scale of these beams as compared to the sky in galactic coordinates. However, CHIME operates 24/7, and that means that over the course of the day, CHIME can end up observing the entire sky that is visible from the northern hemisphere. This large exposure results in a relatively high detection rate for CHIME, averaging at about 3 FRBs per day. The large detection rate has greatly changed the FRB detection landscape. So before CHIME started operating, that is in June 2018, there were about 60 FRBs known. The observing frequencies of these FRBs are shown here in the histogram on this plot. Within a year of operations, CHIME has detected over 500 bursts, bringing the total number of detections to about 600. The bursts that were detected in the first year of operations are included in the first CHIME FRB catalog. These bursts include about 474 one-off FRBs and 61 bursts from 18 repeating sources. The dynamic spectra for 25 of these bursts is shown on the right, with frequency on the y-axis and time on the x-axis. The dispersive delay has been corrected for in all of these bursts. Some of these bursts show complex structures, showing multiple peaks that drift downward in frequency, while others show exponential scattering tails, which are caused by multipath propagation in the inhomogeneous intervening medium. As part of the catalog, we measure the properties of all of these bursts. These properties include fluence, dispersion measure, width, scattering, and the spectral parameters. We also provide localization regions, which are derived based on the detection signal to noise in adjacent beams. And these localization regions are of the order of about 15 arc minutes. While the first CHIME FRB catalog only included bursts that were detected up to July 2019, the CHIME FRB system now has a real-time alert service through VO events. We have been testing this alert service, working with some groups, and have successfully triggered low latency follow-up of several FRBs. This service will become public soon, at which point subscriptions will be available to anyone. So all the FRBs going forward will be shared with the community as soon as they are detected. So back to the catalog. The sky distribution of these 535 bursts is shown in the plot on the top right. In blue are the bursts which are not found to be repeating, while in orange are the repeating sources that are detected with our system. So we first test whether this distribution is isotropic or not. This is an analysis done by Giuseppe et al. And this was motivated by the suggestion from some park surveys that there is a reduced rate of FRBs at low galactic latitudes. So when we plot the cumulative distribution function of the detections of FRBs that we see with CHIME, which is shown in the solid black line here, we find that it closely follows the exposure, which is shown by the dashed black line, indicating that there is no evidence for reduced rate of FRBs at low galactic latitudes. We also cross-correlate the sky positions of all of these FRBs with different galaxy catalogs and find that these FRBs cross-correlate with galaxies in the redshift range of 0.3 to 0.5. More details about this analysis will be presented in a talk in the Cosmological Probe session by Masoud Rafi-Ravandi. So we also analyze the morphology of all of these bursts, and we find that similar to the first repeating FRB source, FRB 121102, that repeaters exhibit complex morphology. An example of such a burst is shown on the right. So repeaters have these multiple peaks, and we also observe downward drifting subbursts. So subbursts, the frequency for which decreases as time progresses. When we compare the repeaters versus non-repeaters, we find that the distributions for most of their properties are indistinguishable from each other, so are consistent when we use the Kolmogorov-Smirnov and the Anderson-Darling tests. However, for two properties, we find that the repeaters and non-repeaters have different distributions. So the plots here show the one-off bursts in green and the repeaters in orange. As you can see, repeater bursts tend to have larger widths as compared to the one-off sources, and they have narrower bandwidth. So repeater bursts seem to occupy anywhere between 50 megahertz to 400 megahertz of our band, while most one-off bursts have a bandwidth that is equal to the full observing bandwidth for CHIME, so about 400 megahertz. So once we have the properties of all of these bursts, we can also plot their DM distribution. This plot is shown here in the left panel. However, this is just the observed distribution of FRB DMs with CHIME and has to be corrected for the selection function. We determine this selection function by injecting signals into the real-time detection pipeline to determine the probability with which a burst will be detected. This selection function is shown here in the top panel. As you can see, we have high sensitivity to bursts with DMs ranging from anywhere between 200 to about 1,000 or 2,000 units. However, we have low sensitivity to bursts with relatively low DMs, as well as bursts with DMs greater than 2,000 units. So once we have the selection function, we can correct the observed distribution by dividing it by the selection function. So on the right, we have the intrinsic DM distribution of the FRB population that is shown here in blue. And we can also repeat this process for other properties. So for example, the scattering time distribution. The observed distribution again is shown here in the left panel in blue. And the selection function that we determine using our injection pipeline is shown at the top. The selection function for the scattering times is a bit different in the sense that we have reduced sensitivity to bursts with really high scattering times. And we are almost missing bursts that have scattering time scales greater than few tens of milliseconds at 600 megahertz, so the center of our bandwidth. So once we divide out this observed distribution by the selection function, we get the intrinsic distribution for the FRB population, which is shown on the right. And as you can see, we find evidence for a large population of events that are highly scattered, so which have scattering times greater than 10 milliseconds. These selection-corrected distributions can be used to determine the FRB rate as well as the fluence distribution index, which will be discussed in a talk by Kaitlyn Shin in this session. So now we can analyze why we are seeing this large population of events that have scattering times greater than 10 milliseconds. To do this, we use a population synthesis framework. This framework simulates the intrinsic properties of FRBs, such as their energies and redshifts. And then we also simulate the scattering and dispersion measure contributions of the different intervening media that FRB signals propagate through. These intervening media range from the Milky Way ISM to any intervening galaxies that the line of sight to the FRB encounters, the intergalactic medium, the ISM of the host galaxy, and the local environment. We adopt different prescriptions for the electron density in each of these media, which allows us to evaluate the dispersion measure of the simulated bursts. We also adopt prescriptions for the level of turbulence in each of these media, so the fluctuation parameter here, which allows us to evaluate the total scattering measure for each of these bursts. So once we have these prescriptions, we can get a distribution of scattering time scales and dispersion measures, and then compare it with the selection-corrected catalog and test different population models using this comparison. So just to give a brief overview of the models that we are simulating. So starting with the Milky Way ISM, we use the NE 2001 model to simulate the DM and the scattering contribution for the Milky Way. The dispersion measure of the intergalactic medium is estimated using the Macarthur relation. As of now, I'm skipping intervening galaxies and the local environment, but I'll talk about those in a bit. As for the host galaxy ISM, we assume FRBs to be located in 3 different types of galaxies: spiral galaxies, elliptical galaxies, and dwarf galaxies. The electron density distributions that we are using for each of these galaxies have been taken from these references. I won't be going over all of these distributions in detail in the talk, but feel free to ask me about these in the questions. As for spiral galaxies, we know that they have a high free electron density. Therefore, if FRBs have different spatial distributions within a spiral galaxy, then that would lead to different DM and scattering distributions. That's why we test 3 different spatial distributions of FRBs within spiral galaxies. These spatial distributions resemble the pulsar and the magnetar populations in the Milky Way. And the third distribution resembles the spatial distribution of short GRB populations. So the first 2 populations here, pulsars and magnetars, are preferentially distributed along the spiral arms, while the short GRB populations are expected to be offset from the galactic centers.
So the 3 minutes left.
Yeah, thank you. The resulting DM distributions for these models are shown here. And as you can see, dwarf and elliptical galaxies have lower DMs as compared to the spiral models. The scattering time distributions for the same models are shown in this plot. And for dwarf and elliptical galaxies, we assume the turbulence to be the same as that for the thick disk of the Milky Way. So once we have the simulated models, we can combine the scattering contributions of the Milky Way, the intergalactic medium, and the host galaxy, and then compare the resulting scattering time distributions with the catalog. So in order to do this, we vary the power law index of the simulated energy distribution to first match the DM distribution with the selection corrected catalog. Once we have the DM distributions matched, we can compare the simulated scattering times with the catalog. When we do this comparison, we find that if we only include the scattering from the ISM of the host galaxy, then we cannot reproduce the observed distributions. So the plot here on the right in blue shows the selection corrected catalog, and all of the other colors show the different models that we are simulating. As you can see, none of these models can match the large population of highly scattered events. So now we need to invoke additional sources of scattering. We start with adding high electron density local environments to all of the simulated FRBs. These environments are modeled based on the observed DMs and scattering for pulsars from the NE 2001 model. And the simulated local DMs range from about 10 to 300 parsec per centimeter cube. So the plots that I'm showing here show something similar to what's shown here, except that this is the cumulative distribution function. In blue is the catalog. And in green here shows a distribution of FRBs with no contribution from the local environment. Once we add the contribution from the local environment, we find that the scattering distribution seems to match a bit better, but is still inconsistent with the catalog. So we go further and increase the minimum local DM to 50 parsec per centimeter cube. So in increasing the DM contribution of the local environment, we end up increasing the scattering contribution as well. However, we now find that this results in a lack of low DM FRBs, although the scattering distribution matches much better as compared to the other 2 alternatives that we tried. This suggests that FRBs inhabit environments with higher scattering per unit DM than those observed for galactic pulsars. We also try other scattering models. So we include scattering in the circumgalactic media of intervening galaxies. This could be caused by cool ionized clumps in the CGM, as was proposed by Vedantam and Finney. We find that after adding this source of scattering, this relaxes the requirement of local environments having extreme properties. As you can see in the 2 plots here, where the catalog distribution in blue is compared to the simulated distribution, we can explain some fraction of this large population of the highly scattered events. However, this distribution is still marginally consistent, and there are a lot of bursts which cannot be explained well by this model. So the main conclusion that is emerging from this analysis is that at least some fraction of the FRB population needs to inhabit environments with extreme scattering properties to be able to explain this large population that we are seeing with CHIME. I leave you with a summary, and I'm happy to take any questions at this point.
Okay, thank you, Pragya. Okay, so Pragya is online to answer questions. We have a few already. So there's one in the Q&A, which is from Pranav Lemay, who says, is there any scientific argument put forward for the narrow bandwidth and wider pulse width of repeaters?
Yeah, so the narrow bandwidth and the wider pulse width could be because of several effects. Like if it was like related to the emission mechanism, then there is one model proposed by Liam Connor et al. Who suggest that if there is variation in the beaming angle, then you could get different pulse widths. But that model currently does not incorporate any information about the bandwidth. On the other hand, we do not see any differences in any other properties of repeaters. So if repeaters and non-repeaters were to be coming from different progenitors, we would expect to see different DM distributions or different scattering distributions, but we don't see any differences in those distributions. So the alternative explanation is that these differences could be because of propagation effects. There are suggestions such as plasma lensing, which causes these widths or bandwidths to be different. Again, there are some issues with that explanation in that we do not see any major DM variations in the properties of our bursts. So as of now, there are a bunch of explanations, but nothing that conclusively explains both of these effects at the same time, and also explains the fact that we do not see differences in any of the other properties of these sources.
Great, thanks. Okay, another question in the Q&A is from Sander, who asks, what distribution did you use for the DM in intervening galaxies? Why did you use a maximum of 300 parsecs per centimeter cubed?
So for the DM in intervening galaxies, we just use the Macquart relation. So the standard deviation on that relation includes any sort of halos that the line of sight to an FRB encounters. And the limit you mentioned, the 300 parsec per centimeter cube, I was referring to that limit for what we assume for the circumburst environment. So for the environment that the FRBs inhabit. And we use that limit because that is just the limit of local DMs that has been inferred for galactic pulsars based on the NE 2001 model. So the NE 2001 model invokes some additional local DM and scattering for some pulsars based on the fact that we see excess DM and scattering for these sources. And the maximum DM invoked is 300. So that's just what we use.
Great. Okay, another question from the Q&A, Charlie Kilpatrick. Why does CHIME have such low detection efficiency for detecting bursts at low DM? Is there any way to improve that efficiency?
Yeah, so that effect mostly is due to human classification. So the fact that we have a lot of RFI candidates at low DMs, and those are hard to distinguish from many astrophysical candidates. The other issue is the systematic uncertainties in the electron density models that we have for the galaxy. So we have this range of events which are classified as ambiguous because we can't say classify their DMs as being high enough to conclusively be located outside the galaxy, which is why we end up missing a lot of these bursts. I mean, we are detecting these bursts, it's just that they are not eventually classified by our pipeline as FRBs because of these two reasons.
Great. And then one more question in the Q&A from an anonymous attendee. How could plasma lensing make spectra narrow?
So I think this is a paper by Cordes et al. From 2016, where they suggest that you could have these caustics which could give, so say if you start with a broadband burst, you would only magnify the signal at certain frequencies, and that's why you would end up with narrow band features in the spectra. But I presume the thing that with plasma lensing was that you would expect drifts in both directions. There is no reason to expect the downward drift in just one direction. So I'm not sure if that model is definitely something that fits to the data. But yeah, you can take a look at that paper if you're interested in more details about that.
Yeah, great. And then one last quick question from the Slack channel from X. If I take this host DM figure literally, and given that we know most FRBs occur in spirals from e.g. Manning's et al. 2021, are we to rule out that they are distributed as magnetars, pulsars, or short GRBs?
So the figure that I showed had a logarithmic axis. So the mean DM that we have for any of these models, magnetars, pulsars, or short GRBs, lies anywhere between 150 to 250 units. And I believe the mean DM inferred for the ASCAP burst is about 150 from the population synthesis analysis that Clancy released a while ago. So I believe those two are consistent. It's just that in the log plot, it looked like a large fraction of the burst had DMs as high as 3,000, but those are certainly a very small fraction, and the mean DMs are consistent with what we have been seeing for the localized bursts we've observed with ASCAP.
Nice. Okay, there are a few more questions coming in the Slack channel, so I encourage Pragya to go have a look there and answer those. And our next speaker, moving on in the program, we have so their next speaker will be Mohit Bhardwaj from CHIME FRB collaboration based at McGill University, who will be talking to us about local universe FRBs from the CHIME collaboration. So Mohit, if you want to try to share your screen and see if yep, that looks great.
Awesome. Thank you very much, Emily. So hello, everyone. My name is Mohit Bhardwaj, and I'm a PhD candidate at McGill University, and also a member of the CHIME FRB collaboration. Today, I will be reporting on 2 local universe FRBs that were discovered by the CHIME FRB collaboration. And thanks to Pragya, who have already provided an amazing overview of the CHIME FRB project. So I'll just get right to the topic and talk about low DM FRBs. Yep. So the first question you may ask is why low DM FRBs are so special, or why I should actually focus and study them. Now, one obvious answer is because these FRBs are located in the local universe, they are the best sources to study the host local environment and in great detail, and also to perform multi-wavelength follow-up to detect any prompt and afterglow emission from the FRB sources that were predicted by some of the suggested models, which is otherwise quite difficult for faraway FRBs, basically because of the limited sensitivity of our telescopes. But equally important, at least for me, is the fact that for nearby FRBs, even few arc-minute localization can be useful to make a meaningful host association, simply because the number density of galaxies, like the host of FRB 121102, the faintest FRB discovered to date, is significantly small due to small co-moving volume in the local universe. This is quantified in this plot. So here you can see on the x-axis, it's the extragalactic dispersion measure, and on the y-axis is the effective localization radius. These 2 curves basically shows the chance coincidence probability given the DMXS, which is a proxy of the maximum redshift, and the localization region. And as you can see, for very nearby FRB, like with the with the extragalactic dispersion measure of around 40 units, even with 1 arc-minute localization, you can say something interesting about the host association. By the way, this chance coincidence probability is estimated basically for finding an FRB 121102 like host by chance within the localization region of size given by the radius on the y-axis. Now, so this is important for us because baseband localization for CHIME FRB events can give us 1 or 2 arc-minute of effective localization region. So it means that for the nearby FRBs, using baseband localization, we can actually associate them to interesting hosts. So with this background, and there are other useful applications of the low DM FRBs, like constraining the luminosity function of FRBs, testing different progenitor models, constraining the DM contribution of the Milky Way halo, and so on. Unfortunately, due to 15-minute time constraint, I'll not be able to discuss these points in my talk, but hopefully in the future talk, I will. So with this background, let's discuss our local universe FRB discovery, the first FRB, which is FRB 2020-01-10E, which is localized to a very nearby galaxy, the Messier 81 galaxy, at the distance of 3.6 megaparsec. Now, just look, so this, first of all, this FRB 2020-01-20E was first discovered back in January 20th, 2020. And that's why its TNS name is 2020-01-20E, because it is the 5th FRB discovered or at least reported to the TNS on that day. Now, using the baseband data saved for 2 of the detected bursts, we localized the FR sky area of around 14 arc minute square. Now, just by looking at the low DM excess value, it is clear that the FRB is within the local universe, and we estimate the maximum redshift for this FRB to be around 0.03. And if you look at its low RM excess or rotation measure excess, we inferred that it does not have a dense circumverse medium like one we found in the case of FRB 1102. Now here, I basically show waterfall plots for three bursts of the FRBs that we reported in the paper. Two of them, we saved the baseband data. So one interesting observation to note here is that if you look at the FRB 2020 or 120E baseband waterfall plot, you see this downward drifting substructure, which is thus far exclusively seen in the waterfall plots of repeating FRBs. So with this discussion so far, you may say that, well, this source looks like an extragalactic repeating source. So let's find its host galaxy. But here comes a catch. Low DM FRB, though they are very interesting and promising sources, it is always difficult to assert conclusively that they are indeed extragalactic, mostly because of the high uncertainty in the Milky Way and its halo DM contribution. Although I should acknowledge that the Milky Way DM models do take into account different observations, but Milky Way halo models, on the other hand, are largely based on theoretical assumptions about the halo and include less model independent observations. And it's basically because of the paucity of useful observations. For example, in this GIF, you can see that how the final classification of the FRB shown in the title of this plot changes if we assume different DM contribution of the Milky Way host and halo. So in the paper, therefore, we actually discussed different ways to tackle this problem. So the conclusion we made in our paper is the extragalactic origin is definitely more promising, mainly because the first thing is there is no plausible galactic counterpart we found in our search. And next, and more importantly, in our host galaxy search, we found M81, an early type spiral galaxy at the distance of 3.6 megaparsec, close to the FRB localization region. Now, that's not just satisfied the observed low DM excess, but also the chance coincidence probability of finding an M81-like galaxy that close to the FRB localization region purely by chance is less than 1%. Now, the most intriguing twist, I should say, in the story of this FRB origin comes when the precise EVN collaboration localized this FRB to an M81 globular cluster, which actually we have identified and showed in this plot as source 3. Now, why this observation is bizarre? Because if we believe that repeating FRBs are produced mainly by young magnetars that are formed by prompt formation channels like type 2 supernovae, superluminous supernovae, we do not expect them to be found in such an old stellar system. You can read more about this discovery in a very interesting paper led by Franz Christian, and here I show the archival link. And also, it is important to point out that this kind of analysis can only be done for very nearby FRBs, because it is very hard to identify globular clusters and galaxies outside the local volume. For instance, even Hubble can barely detect a globular cluster at a distance of 30 megaparsec. And that's another reason why it is important for us to discover more nearby FRBs. And with this node, actually, we also found another local universe FRB that especially satisfied this constraint. So this paper is submitted to AbGL and is right now in review, by the way. Now, it is FRB 2018-1030A. It was first discovered back in 2018 by the CHIME FRB collaboration and was reported in our 2020 discovery paper, along with 7 other repeating sources. Now, what makes this FRB interesting is the fact that its DM excess is, again, quite small. It's around 20 to 30 units when after we remove the fiducial contribution of the Milky Way disk and halo. And so this suggests that the FRB is quite nearby. And fortunately, we saved baseband data for 4 of its bursts that we detected back in 2020. And using them, we basically localized this FRB to a sky area of around 5.3 arc minutes square. Now, in this plot, you can see 90% confidence localization region of the FRB as cyan ellipse. And now with this localization, the galaxy that instantly takes your attention is NGC 3252. It's a spiral star-forming galaxy located at the distance of 20 megaparsec. So basically within our supercluster Laniakea. Now, to check the robustness of this association, we first estimate the chance coincidence probability of finding this galaxy, and we found it to be less than 0.25%, even after accounting for the look elsewhere effect, because CHIME is anyway detecting many sources. Now, independent to this low PCC argument, we also identify all plausible galaxies within the FRB localization region, which if exist at the maximum estimated redshift for this FRB, which is around 0.05, it would be at least 5 times fainter than the faintest FRB host discovered to date, means FRB 1211 or 2. And then we basically estimate the spectroscopic redshifts for all those galaxies. And we found them for all those galaxies, the spectroscopic redshift is significantly larger than the maximum estimated redshift for of FRB 2018-1030A. So therefore, both of these analyses strongly support the association of the FRB with NGC 3252. Now, here I basically showed the fitted spectral energy distribution plot of NGC 3252. It's similar to a typical star-forming galaxy. And we use this modeled SAD to estimate different physical parameters and other interesting properties, which is discussed in detail in the paper. So I'll urge you to read it as soon as it will be available on archive. Now, there are a few important implications of this localization. So the first thing is we basically estimate, this is a nearby FRB, and I said it's a very promising source to constrain the Milky Way halo contribution along the FRB sightline. So we estimate the halo contribution in the sightline to be around between 19 to 55 units. This is the 90% confidence interval we found using a Bayesian analysis. And second, using the 3 local universe FRB, we have detected, the CHIME has detected to date, we basically estimate a lower limit on the volumetric rate of these luminous less luminous repeating sources, and found that the rate is at least 100 times larger than the core collapse supernova rate, which basically suggests that the low luminosity FRBs, if you detect, is more likely to be repeating sources. And last but not the least, based on the observed co-moving number density of repeating FRBs, we argued in the paper that it is unlikely that all repeating FRBs are produced by young millisecond magnetars, young basically 10, 100 to 1,000 years that Metzger and others actually stated or assumed in their models. And that are formed primarily by cataclysmic events like superluminous supernovae, long and short GRBs, and even accretion-induced collapse, white dwarfs. And therefore, if you include them, then we actually need another model which is more dominant in order to produce or satisfy the observed FRB volumetric rate.
We'll hit 3 minutes.
Sure, thank you. Now, I also compare, so we also compared all the known repeating FRBs, which are showed here in the mass versus star formation rate plot. And in the background, I basically plotted all the star forming galaxies with known redshifts and different spectral lines in the SDSSDR4 catalog. Now, it is interesting to note that all the repeating FRBs are either FRB hosts are either irregular galaxies or spiral galaxies. And most of them are close to the star-forming galaxies main sequence, except these 2. So this one is M81, and this one is the host of R3 or FRB 2018 or 916b, and these are likely Green Valley galaxies, means galaxies that are transiting to a quiescent state. Now, so now you may say that, well, M81 repeater is technically localized to a globular cluster. So how star formation rate is important here? And that is an absolutely correct, I think, point to make. And therefore, we actually need larger sample to say something meaningful about the host repeating FRB host population. Now, lastly, I'll just tell you that CHIME FRB is actually filling the phase space between FRBs and galactic pulsars. So here is a beautiful plot from Nemo et al. Paper, where x-axis is the transient duration and y-axis is the spectral luminosity. And here I basically overlaid FRB 2000, M81 FRB burst and FRB 2018 1030A burst. And you can see that these are basically narrowing down the gap between galactic sources and the repeating FRBs. And these are actually very important, especially if you want to constrain a low luminosity cutoff for FRB, and which actually many models have a well-defined value. So therefore, by constraining that low luminosity cutoff, you can also constrain the possible emission mechanisms. So well, this brings us to the end. Here's my summary slide. And now I would like to take questions. Thank you very much for your attention. That's all.
Thank you, Mohit. That was a great talk. Okay, so we have a few questions, some in the Slack, some in the Q&A. So the first question in the Q&A is from Sergey Popov. Just an obvious comment. The probability to have a nearby galaxy in the localization area of an FRB is very non-uniform over the sky. So the numbers for the probability you showed in the plot are even smaller if it is not direction towards the Virgo cluster or something like this, as it is less than 100 megaparsecs galaxy distribution and it's not uniform.
Absolutely, agree. It's because it's more conservative. We just focus that in the paper. But good point.
Yeah. Okay, and then we have questions in the Slack channel from X. What is the path posterior probability for NGC 3252, I think, being the host for FRB 2018-1030A?
I didn't estimate that using path. So one reason is there is no other plausible galaxy, because all other plausible galaxies we found within the localization region are beyond the maximum redshift. And if you use the 10%, what is like the fiducial value that is invoked in the Bayesian analysis, you actually found even smaller chance coincidence probability, just because in the localization region, NGC 3252 actually occupies larger area. And second thing is, I feel that the Bayesian analysis it's excellent way to estimate the chance coincidence probability, but we still need more data to constrain the priors, because as you can see, globular cluster ideally in principle can be found anywhere within the virial volume. So in that case, assuming that the density would go down as a function of the galactocentric radius is an assumption. So I think we should wait for more data to get to that point.
Great.
But yeah, it will be smaller, definitely, if I use path.
A question in the Slack from Clancy. The M81 paper hinted at approximately a dozen other low DM FRBs. Can you give us some hints as to whether these may or may not be associated with nearby galaxies? Please wildly speculate and ignore that you have many other collaborators in the audience.
Thank you very much for the question. And without leaking any sort of non-public information, I would say that there are a number of low DM FRBs that we are currently working on. And so soon you will try to publish them as soon as possible. So yes, there are many low DM FRBs within the local universe that we found, and we potentially associate them with the host galaxy, but that work is currently under, like, we're right now working on that. So maybe in near future, we'll publish that paper soon.
Yeah. Okay, and then one last question from the Slack from Surya Bhattapudi. Are there any globular clusters in NGC 3252? Would it be likely for this FRB to be also like FRB 2020-0120E, i.e. come from a globular cluster?
Yeah. Who asked this question? I'm sorry.
Surya.
Okay, that's a great question, Surya. So one thing is, because after M81 FRB, I think we should always open with this possibility, because M81 is a spiral galaxy. It's not an elliptical galaxy. And this is also a spiral galaxy, though you can compare and contrast in different vectors. But it's possible to have globular cluster. And globular clusters are not only located at the outskirt of the galaxy. We have a stellar halo, which is close to the center, and we have globular clusters there as well. And because the DM excess is low and the expected host contribution is small, so one can speculate that it might be associated with the globular cluster. Unfortunately, the archival optical data is not is not deep enough to constrain that. We need Hubble data. Now, just to give quantify this point, at I think 20 megaparsec, the distance modulus is around 36, and typically the expected globular cluster V-band magnitude is -8. So you need 36 minus 8 means 28 apparent magnitude depth in V-band to actually detect a similar globular cluster close to NGC 3252, which is right now only possible with Hubble telescope. So I would suggest we should wait for EVN collaboration again to localize this FRB to milliarc second, and then apply Hubble time and then see if there is a globular cluster within the localization region. I hope that answered your question.
Yeah, that's great. Thanks. Okay, so thank you, Mohit. That was a great talk. We will now move on to the final talk of the session, which is a talk by, it will be a recorded talk, but Kaitlyn is online to answer questions afterwards. So again, please put your questions in the Q&A. And so this is Kaitlyn Shin from MIT, who will be talking about FRB population distributions from the first CHIME FRB catalog.
All yours, Kaitlyn.
Awesome, thank you. Okay, so hi, I'm Kaitlyn, and I'm a graduate student at MIT working with Professor Kiyoshi Masui and the CHIME FRB collaboration. And today I'm going to be talking about results on FRB population distributions from the first CHIME FRB catalog. So since I'm directly following another CHIME FRB Catalog 1 talk, I'll keep this background extraordinarily brief. So as a quick refresher, the first CHIME FRB Catalog sample has detected 535 FRBs in roughly the span of a calendar year, and the sample includes 61 bursts from 18 repeating sources. And for each of these bursts, we've measured associated properties such as fluence, DM, scattering timescale, and intrinsic pulse width. So now there are certain questions about distributions of properties that are easy to ask but hard to answer. For example, how are the observed brightnesses of FRBs distributed? And also, what is the overall sky rate of FRBs? And the reason why these questions are so hard to answer is because we can't take our observed measurements at face value. We need to account for selection effects if we want to properly answer these questions. And this is something that the first CHIME FRB catalog sample has done. And so, kind of as I hinted before, the observable properties that we're studying are the fluence, the dispersion measure, the scattering timescale, and the intrinsic pulse width. And the key to kind of studying these properties while accounting for the selection effects is the injection system. And so for more details on the injection system, definitely check out the poster and or lightning talk by Marcus Merrifield. So what we do with this injection system is we inject events into our real-time detection pipeline with a wide range of parameter values so that we can calibrate our observed selection function or selection effects as a function of all these FRB properties that we are considering. And so in order for our injection sample and our observed catalog sample to be comparable, we have to cut any bursts from the catalog 1 sample that we think has a selection effect that's not captured by the injection system. So we can take signal to noise as an example. In the CHIME FRB catalog, all these real bursts basically undergo double human verification, where we look at these bursts and we're like, is this real or is this just noise? So it's entirely plausible that for lower signal to noise bursts, humans might accidentally miss some of these bursts, misclassify them as noise or something. You know, we're only human. And obviously this is a problem that the injection system just doesn't run into. And so how do we quantify this human incompleteness bias? We just can't.
And so one of the cuts that we make to the catalog 1 sample is we cut all events below a signal to noise of 12 because we say it's only a signal to noise of 12 or higher that we humans are complete and can catch all the bursts the same way the injection system catches all the bursts. So now we can combine both the injection sample and the observed catalog sample to fit a fiducial model that reasonably describes the FRB property distributions. And for this first catalog sample, we're making a key assumption, which is we're assuming that the properties of these FRB properties that we measure are intrinsically uncorrelated. And this allows us to assume that the intrinsic joint distribution of all of these properties neatly factorizes into intrinsic individual distributions. And of course, in principle, all these intrinsic FRB properties should be modeled and fit simultaneously if we want to be fully self-consistent, but that's something that we're going to defer to future work. Now, what this model doesn't assume is that the selection effects factorize, or in other words, the simplified fiducial model, this enables us to deal with correlated selection effects of the observed properties. So what do I mean by a correlated selection effect? An example, you can take DM smearing as an example. So for a lower DM burst, that might be a narrow burst. If it, like within a frequency channel, it might not have much of a temporal smearing response. But for a higher DM burst, because it travels so fast from high to low, top to bottom frequencies, it could induce a temporal smearing response within a channel, which means when we average over that frequency channel, the observed burst might appear to be wider than it actually is, but then when we subtract out the smearing effects, we might accidentally miss the high DM narrow burst. But if this high DM burst is intrinsically wide or has an intrinsically large pulse width, the observed pulse width is no longer dominated by the temporal smearing, and so we're less likely to miss this high DM burst. And so this is kind of what I mean when I say there's a correlated selection effect, and in this case, it's between the DM and the intrinsic pulse width. And so from the injections in the fiducial model, we can calculate selection functions, and we do calculate selection functions for the DM, the scattering timescale, and width distributions. And something that I really want to reemphasize is that the selection function of one property, such as DM, depends on how the other properties are distributed. And that's why we have to fit this fiducial model so that we're able to kind of deal with these properties together. So I'll start with the results for the scattering distribution. This is scaled to 600 megahertz. And so what we see in the main left-hand panel is the raw catalog distribution before compensating for selection effects. And then on the right is the distribution after we compensate for selection effects. And the fiducial model is overlaid on top of the distribution as well. In this case, the fiducial model for each of scattering, DM, and width are assumed to be a simple log normal distribution. And in the upper left-hand panel, we can see the selection function is plotted. And so as Pragya had mentioned in her talk just earlier, we see a severe selection bias against events with a high scattering timescale above 10 milliseconds. And this is reflected in the shaded region of the histograms. And if we look in the left-hand panel, for example, the raw catalog distribution, we see just a handful of highly scattered events, say the last two bars of this histogram. But if we look at the right-hand side plot, we see that in this area, the distribution is poorly constrained. And this is, so basically what our injections is telling us is that in order for the CHIME telescope to have even detected this handful of highly scattered bursts, there must have been an even larger population of undetected bursts that have high scattering. And the uncertainty is large, of course, but it does seem like the bursts are there. And so to explain this amount of scattering, it does suggest that these FRBs must inhabit environments with strong scattering properties. And of course, I'm sure you all recall the talk that Pragya gave 20 minutes ago for more on this interpretation. So now I'm showing the results for the DM distribution. And if we look at the selection function in the upper left panel, it seems that while we are biased both against lower DM and high DM events, we seem to have larger biases against low DM events from, say, detrending and flagging effects, rather than against high DM events, which might occur because of the DM smearing example that I gave earlier. And so now here I'm showing the results for the intrinsic pulse width distribution. And once again, if we look at the selection function, it appears that we select against wide events. Yet when we look at the main histogram distributions of the panel, we see that unlike the scattering distribution, there doesn't seem to be much evidence for a large unobserved population of bursts with intrinsically large pulse widths. So now I'm going to talk about the fluence distribution of FRBs, including a measurement of the absolute rate on the sky. So we can model the cumulative fluence distribution as a power law parameterized by this power law index alpha. And in the Euclidean expectation, the alpha index is -3/2. And the measured power law index values for this FRB brightness distribution for FRB brightness distributions that we see in literature are pretty discrepant, even after taking into account error bars, and I've listed a few examples there. So I guess, where does CHIME FRB come in? So in order to estimate both alpha and the all-sky rate with our first catalog sample, what we do is we fit the joints distribution of fluence and DM. And there's actually a little subtlety here. We actually use signal to noise as our observable proxy for fluence. And that's because we can forward model our signal to noise measurement with the injections, but that's something that's hard to do with fluence measurements because all that happens in an offline pipeline. So anyway, we then draw MC-MC samples from this posterior distribution, and we find an alpha value of -1.4 plus or minus about 0.1, which is consistent with this Euclidean expectation, as well as an all-sky rate of about 800 FRBs per sky per day, and this is above a fluence pivot of 5 Jansky milliseconds, scattering timescale of 600 megahertz, and above a DM unit of above a DM value of about 100 units. And so this Euclidean expectation only really holds if we include sources at all the distances, but we would expect there to be distance scale induced correlations between fluence and DM. And so we can take this kind of generic toy model illustration that I've shown here on the left, where we have this energy distribution. It's concave down so that the total energy doesn't diverge. And so for more near sources or lower DM sources, we would expect to preferentially sample the lower energy, shallower part of the luminosity function. And likewise, for further away higher DM events, we would expect to preferentially sample the higher energy, steeper part of the luminosity function. And so when we split our sample into a low DM sample and a high DM sample, and we do the analysis where low DM and high DM, the split is at 500 DM units, which is close to the median DM value of our sample. We see on the right hand, so if the left is a toy model, the right is actual data. And we see on this right hand plot significantly different values of alpha between the low DM and the high DM samples. And so as expected, the low DM sample has a shallower alpha value of about -0.9, and the higher DM sample has a steeper alpha value at about -1.8. So
three minutes left.
Thank you. And so it's clear that this joint distribution of dispersion measure and fluence holds a lot of information. And we can fit a more physical model to the intrinsic distribution, similar to what Clancy James presented earlier this session, to get information about the underlying FRB luminosity distribution as well. And preliminary work is already underway for this. And so kind of to wrap up, with this first CHIME FRB catalog, we've detected 535 new FRBs. And not only that, we've also characterized the selection biases, which is useful for properly measuring the intrinsic population property distributions. We've also found evidence for a large population of highly scattered FRBs, which is strongly suggestive of some FRBs having their origins in highly scattered environments, such as, dense turbulent ones. And we've also measured an alpha value consistent with Euclidean expectations, as well as seeing evidence for distance evolution of the brightness function. And I've also finished a little bit under time, but I'm happy to take any questions.
Okay, fantastic. So we have Kaitlyn on the line. So anyone who has questions for her, please go ahead. I'm monitoring the Q&A. It looks like we already have a question on Slack from Clancy. So he says, with regards to your slide 13 on your high versus low DM samples, do you really need a changing slope in the luminosity function to produce different values for alpha for high and low DMs? Doesn't this arise naturally when DM is positively correlated with distance, virtually regardless of the intrinsic luminosity or energy distribution?
So, yeah, it does arise naturally when there's a correlation, but the interesting thing here, I think, which is something that I didn't go into the talk, but I believe is in the paper, is that if you don't account for the selection biases when you measure this, when you measure these alpha values, you might accidentally get a completely different result. And at least in the paper on the archive, this is definitely the following figure. And so kind of this is something that I've presented as when we do correct for this, when we do take into account their selection function, we see what we expect.
Nice. Okay, thanks. And then we have a question in the Q&A from Pranav. If possible, can you shed some more light, or can you shed some more comments on the distance evolution of the brightness function?
So I think that's we're just sampling, I guess. I mean, I guess this is also just the kind of correlation for the DM and distance. And so I think this evolution or distance evolution of the brightness function basically means, I guess I'm trying to find a way to word this that isn't completely circular. And so we have a distance evolution of the brightness function, which is basically this is just indicating that when we sample different parts, or when we look at our different samples of FRBs based on their DMs, we're sampling different parts of the energy distribution. And so this is kind of just like distance evolution, I guess. I'm not really sure if this is kind of what you're looking for, but
well, we can always continue the discussion on the Slack channel if there's more interest in elaborating. So that's good. Okay, so I don't think we have any other questions in the Q&A. I definitely encourage people, if they have more questions for Kaitlyn, to ask them in the Slack channel. But I think we are very close to the hour, so we can go ahead and conclude the session. Thank you so much to all of our speakers, both recorded and live, and the people who did it twice. We appreciate it. If you have questions for any of the speakers, or you are interested in exploring the topic more, I encourage you to put that in the FRB 2021 Plenary 1 Slack channel. And if there's anything that you'd like to elaborate on more in a larger discussion, then try to organize something at an upcoming coffee over at the Gather Town. So with that, I think we can conclude. And thank you very much for everyone for attending. I think we had something like 90 participants during this session. So thank you for joining. The next session will be session 3A. So please check the schedule for the start time.